at the end of the last session, which was only an hour ago, so hopefully you haven't forgotten, we're at the stage where we could draw a straight line in any direction, and we looked at how to modify Bresham's algorithm to do so, and this was the result. Okay, so that's line drawing, and Bresham's pretty much, you know, we haven't got a method better than Bresham since the late 60s, so we'll keep with Bresham. Another question or another problem which we may have is to do with circles and the ability to draw circles. And that's what we're going to look at for this lecture, and also the distinction part of assignment 8. Okay, the first thing I want to sort of mention about circles is the idea of symmetry. So here we have a circle, your standard x and y axis, circle centered at the origin. Okay. What I have here is, this is what I'm going to call the first octant. Okay, and the first octant is the region between the 12 o'clock point and the point where the circle intersects with the line y equals x. So that's like a 45-degree line there. That is the first octant. Now the reason I've highlighted that is that if we know the coordinates of a point on the circle, and let's say they're x and y, so we know the value of x, we know the value of y, we automatically know the value of the other 7 points around the circle in the other 7 octants. So for example, we know x and y. If we reverse x and y to give yx, we know that must be a point on the circle. If we then negate or change the sign of x, we'll have that point. If we flip these two back again, we have this point, and if we negate the x, we have this point, and so on and so forth. So the point being, no pun intended, that once we know the coordinates of one point in the first octant on the circle, we automatically know the points of 7 other points on the circle without having to do any work. We know x and y, all we have to do is have combinations of plus and minus x, plus and minus y, and plus and minus y, plus and minus x. So what this means is when we draw circles, we only have to deal with this bit here, because all the other 7 octants around the circle, we know what they are. And so this leads on to the idea of this sort of function. This is a little function in MATLAB. I've called it circle points. And essentially, if you're given a raster array, and hopefully we know what that is by now, x and y are the coordinates of a point on a circle. C is the center of the circle, and color is just whatever color we want to color the circle in. We can then illuminate 8 pixels. So given that information, just x and y is a point on the circle. Okay. We then know the positions of 8 points on the circle. So that cuts down on the amount of work we have to do by 7/8. You only have to do 1/8 of the circle to draw the entire circle. Right, so this brings us on to what is known as the midpoint algorithm. And this is very similar to Bresham's algorithm. What we want is we want a method that chooses or tells us which pixel to illuminate on a circle without having to do any form of real number arithmetic. So we're only dealing with integers again. Now, we're going to be dealing with the first octant, which is the 12 o'clock position to around about, well, 1:30. Not doing the clock. The 12 o'clock round to where y equals x. So what we have is we have this sort of simplified diagram. Here, this blue pixel, we're assuming it's already been illuminated. We know that that's a pixel on our circle. What we then do is we step to the right, and we have a choice between the pixel to the east or the pixel to the southeast. Okay. And a similar way in which we did before with Bresham's algorithm, what we do is we determine an error which is between the idealized image, which is the circle, and the midpoint between these 2 centered pixels. Okay, so these points are at the center of the pixel. That midpoint is there. So this epsilon is the error between the circle and that midpoint. Hence the name midpoint algorithm. And that the y coordinate of that midpoint is simply our yi, which is our pixel we just illuminated, minus a half, because the distance between these 2 points here is 1. Okay, so if this is positive, we choose this pixel to the east. If it's negative, we go to the southeast. Weird. Okay, so Brescian's algorithm, as its base, used the Cartesian equation of the line. So the midpoint algorithm uses the Cartesian equation of the circle. A circle centered at the origin with radius r follows this equation: x squared plus y squared equals r squared. Essentially, Pythagoras' theorem, if you think about it. So what we say is we define that the error between any point x, y and our circle is, just rearrange this, okay, we get x squared plus y squared minus r squared. So a point bang on the circle would have an error of 0, and so if we subtract r squared from both sides, we get an error of 0. A point somewhere off the circle is going to have an error, that's either going to be positive or negative. So this is very similar to Brescian's algorithm. We're looking at an error and we're comparing its sign, and whether it's positive or negative depends on which direction we go. So the next pixel, if the error is positive, we just go to the east, which means we don't change the y coordinate, we just step across. Or if the error is negative, we go to the southeast. So as well as adding 1 to the x coordinate, we subtract 1 to the y coordinate, so we're going down. The error is calculated as the difference between the idealized circle and the pixel center. And we start at the 12 o'clock position. Okay, so assuming, with all of this derivation, we're assuming our circle is centered at the origin. So if we start at the 12 o'clock position, we're starting at 0r, where r is the radius. And we use x as a driving axis, and we continue until our x coordinate is equal to our y coordinate. Because we're only calculating it in the first octant, we then use circle symmetry to calculate it in the other 7. Very, very clever algorithm, this. Okay, so let's have a look at the algebra. As before, we remember with Brescian's, we didn't calculate the error each time, we just added something to the error, a change in error. So the change in error we're going to look at is between the pixels at x plus 1, y minus a half, so that's at the next midpoint, and the midpoint after that. Okay, so with Brescian's, we looked at the error at the next 2 pixels minus the current error. With midpoint, it's slightly different. This is the error at the pixel 2 steps time, so 2 steps to the right. This is the error at the pixel at the midpoint 1 step to the right. So the coordinate of the midpoint 1 step to the right is simply x plus 1, y minus a half. Now the coordinates of the error, the coordinates of the midpoint 2 steps to the right is x plus 2. Then we've got this y subscript I plus 1. We don't know what yi plus 1 is. So again, we're going to update it based upon what choice we made. Put that into the expression for the error. So the error was x squared plus y squared minus r squared. So there's your x squared. So x was x plus 2. So there we have. There's your y. That's y squared minus r squared. Minus x squared minus, oh, there should be a squared there, y squared plus r squared. Okay, so the r's are going to cancel out. That minus r squared is going to cancel out with a plus r squared. Okay, so if we expand out all of these squares, okay, just a lot of algebra that, well, too much, just 4 quadratics to expand. Okay, and you can see there's also going to be some cancelling out. There's a plus a quarter there, minus a quarter, etc. Okay, so just do that. If we cancel out, we get to this. So 2x plus 3 plus y plus 1 squared. Now I don't know, or we don't know what that yi plus 1 is. It's going to be dependent on a choice we make. Minus yi plus 1. Minus y, which we know, minus y squared, sorry, which we know, plus 1. Okay, so this is the expression for the change in our error. Okay, so very similar in sort of procedure to the Brescian's algorithm. So we got that choice. Okay, so we make a choice of what pixel we choose. Okay, so if the pixel to the east is chosen, we don't change the y coordinates. We've just got a cross. So therefore, our yi plus 1 is simply equal to yi. So if we had yi plus 1 squared minus yi plus 1. So you can see that cancels out with that yi squared. That yi cancels out with a plus yi. So we're left with 2x plus 3. So whatever your x coordinate is, times by 2, add 3 to it. That's your change in error. If the pixel to the southeast is chosen, we subtract 1 from our y coordinate. So we have, instead of this yi squared, we have yi minus 1 squared. And likewise there. Okay, so we multiply them out, do some cancellations, and we end up with 2x plus 2y plus 5. Okay, so we've got our change in errors. Notice these are x and y are always going to be integers because they're pixel coordinates. These are all integers, so we're just dealing with integer arithmetic. We also need an initial error. We need an error for the starting pixel. So we're going to choose the difference, or the initial error is the difference between the 12 o'clock position and the first midpoint. Okay, so 0 r and 1 r minus a half. So that r minus a half is your y. Okay. So we're going to do the same. So our initial error is going to be the difference between those 2 points. Okay, so that's your x squared plus y squared minus r squared. So that one, that's your x squared minus y squared plus r squared. And the r squares cancel out, and we get 5 over 4 minus r. Everything good, apart from 5 over 4 is not an integer. It's ruined it. Okay, we had a nice sort of method set up. Our change in errors were all integers. Along comes the initial error and ruins the party for everyone. Okay, so that's ruined it. 5 over 4 is not an integer. Fortunately, it's a dead easy fix. Okay. All we do, okay, here are the error expressions. So that's your initial error. So that's your error when you first start. That's your error, or your change in error if you went to the east, and that's your change in error if you went to the southeast. All we need to do is multiply them by 4. So we multiply the first initial error by 4, we simply get 5 minus 4r. The change in errors also get multiplied by 4, and we've got integer-only expressions. Remember, it doesn't matter what the value of the error is. We're only looking at the sign. We're only looking at whether the error is positive or negative. Okay, so here's the algorithm. Again, this is similar to Brescian. What we need is our raster array, circle center coordinates, so we need to know where the center of the circle is, the radius of the circle as well. And the center and r need to be integers, because we're dealing with pixels. So if you happen to have non-integer values, you have to just round them. We start with x equals 0, y equals r, and our initial error 5 minus 4 times r. And whilst our x coordinate is less than or equal to our y coordinate, we invoke circle symmetry. Okay, so this is, we know what x and y is, so we illuminate x, y, and then we illuminate the 7 other equivalent points. If epsilon is less than 0, the the pixel to the east is chosen, and we add on 8x plus 12, because that was a change in error. Notice that in this case, a change in error isn't constant like it was for the line drawing. Okay, it depends upon your values of x and y. Okay, so we can't pre-calculate that. We have to calculate that in each step. Okay. If it's positive, we go to the southeast. Okay, and we subtract 1 from y, and then we increment x. Okay, so quite similar to Brescian's algorithm. Okay, and of course, if you want it as a flow chart, okay, you could. It's the same thing. It's just some people find it easier to understand it when it's in that form. Okay, there's the output. Okay, I just happened to draw 4 concentric circles. Just going to show you the MATLAB code for this. Okay, I'm not going to show you too much of it because it's part of your assignment. Okay, but this code draws the circles. So what I did there, nx and my is my raster. The color of my circle, I wanted it blue, so 0, 0, 1 is blue. And the center of the circle is at 50, 50. Initialize a raster array. So 1s, ny, nx, and 3 creates my raster array. Because it's all 1s, it's all going to be white. If I wanted it black, all 0s. I don't mind if it's black or white in your assignment. I chose to draw 4 circles, and the radius is just 10 times I, so the radius is 10, 20, 30, and 40. And then I coded up a midpoint algorithm, plot it, and then I plotted it using the normal way. And I'm just going to show you down to there, because I don't want to show you anymore, because that's your assignment. That was my function definition for this. So the function input raster, C, R, and color, and outputs the raster. So at each time, this just adds on the circle to the current raster. And there you go. There it is. And the circles, they're not brilliant, obviously, because it's only an approximation of the idealized image, but paint's all out. You know, if you do any sort of drawing package or anything, and you say, right, I want to draw a circle, your computer is doing the midpoint algorithm. Okay, so this brings us on to the final activity, right, which is also the hardest one. So hopefully I don't make a mistake. Oh, you can't see anything yet. Zoom out a bit. So here I was giving you a larger raster because we're drawing a circle and it needed to be larger. Okay, use a midpoint algorithm and circle symmetries to draw a circle centered at the pixel 10, 10. So what I'm going to do is I'm just going to mark the center just to help us a bit. That's my center pixel with a radius of 9, okay, on the axis below. So the first thing I need to do is set my x and y coordinates. So x equals 0, y equals 9. Note that our x and y is relative to the center being at 0, 0. Okay, when we want to plot it, we have to then add our center coordinates to our x and y coordinates. And our initial error is 5 minus 4r. That would be 5 minus 4 times 9, which is 5 minus 36, which is minus 31. I'm going to resort to a calculator, I'm afraid. All right. Okay, so that's our starting values. What we do straight away is we plot. Okay, I'm going to plot the x and y. So from the center, I'm going to go 0 across in the x direction, but 9 up in the y. 1, 2, 3, 4, 7, 8, 9. So I'm just going to use a cross. That's my first point. Now I'm going to use circle symmetry. So it was centre plus x, which is 0, centre minus x, which is 0, so that's my 2, 1. Then I'm going to flip x and y around. So I'm going to have centre plus 9 in the x direction, centre plus 0 in the y direction. So that means I go across 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got one there, and I've also got 1, 2, 3, 4, 5, 6, 7, 8, 9. There. And there is another one down here. Okay. So on the first one, using the circle symmetry, I could illuminate those 4 pixels. Now here, our epsilon is minus 31. So that's less than 0. So if it's less than 0, it means we go to east. So we go to the east and we update epsilon. So we have minus 31 and we update it plus 8x plus 12. 8 times 0 plus 12. So that'll be minus 16, I think. Minus 19, sorry. And because we've gone to the east, our x has increased by 1, but our y hasn't changed. So from this 12 o'clock pixel, we go to the east. Okay. So we're there. Invoke circle symmetry. Well, if I've gone to the east, I can also, if I do a line of symmetry about that axis, I could also go to that one. And I could do the same down here. I could do the same here. Okay. Does that make sense? I can just do those symmetry. Okay. In this case, our epsilon was minus 19, which is still less than 0, so go to east again. Okay, we go to east. Okay, but we have to update our error. And our error is the current error times our x coordinate, which now is 1, plus 12. So we've got minus 19 plus 8, that's minus 11, plus 12, so that's going to be 1. So that's, again, so from here, we're going to the east. Invoke circle symmetry. X equals 2, y equals 9. Okay, but now our error is 1. You can see, so that's the error we have now. It's positive. So this means finally we go to the southeast. Okay, and we update our error. So when we update it, we add 8x minus 8y plus 20. So we have add 8 times x. Now x is 2 minus 8 times y. Y is 9 plus 20, which is minus 35. So we had to go to the southeast, so this time we subtract 1 from the y value. Okay, so if we subtract 1, go to the southeast, we've got that one there, got that one there, and we invoke circle symmetry. Okay. Our error is now minus 35, which is obviously negative, so we go back to going to the east again. Should make that less like an epsilon. Okay, so epsilon is now minus 35 plus 8 times x, we've got 8 times 3 plus 12. Okay, so it's minus 35 plus 24 plus 12. Oh, sorry?
1.
Yeah. Oh, yes, it is. Yeah, I typed it in wrong on my calculator. I was getting 11. Okay, so now we're at 1, and we had to go to the east. So we've got x equals 4, y equals 8, which is that one there. And again, do your circle symmetry going around. Okay, so epsilon's 1 again, which is positive. So this time we go to the southeast. And we add 8 times x, which is 4, minus 8 times y, which is 8, plus 20. Which is minus 11. All right, so that was going to the southeast. So that's 5 and 7. Is that one? That one? That one? That one? You can see it's almost going to join up in a minute. Okay, so error is minus 11. Negative, therefore go to the east. And for what it's worth, we don't need it, but I'll update the error. So minus 11 plus 8 times 5 plus 12. Minus 11 plus 40 plus 12 is 41. So we had to go to the east, so x equals 6 and y equals 7. That one there, that one there, that one there, that one, that one, that one, and that one. And we finished our circle. If we went to one more, you just flip that one to there. So might as well finish up there. Okay, so a little bit more involved than Brescians because you couldn't pre-calculate the change in error. The change in error is based upon what our current values of x and y are. But all the numbers are integers, and all we're doing was comparing your error to 0, whether it's positive or whether it's negative. Right, you okay with that? Okay, just in case I did make a right sort of balls up with that one, because it is quite tricky. Okay, so this is what we just done. The red blodge spot is the centre, that's a circle, and that's what we've done. Obviously, the more pixels you have, the smaller each pixel, the more like a circle it will look. Okay, but that's circles. Okay, I'm going to move on to ellipses now. Now, ellipses is not something I'm asking you to do in the assignment, okay, but just drawing circles does limit us a bit. In sort of real applications, ellipses are far more useful. And I'm going to talk about doing ellipses, but this is not something I'm going to ask you to apply. So don't sort of worry too much about it. Okay, this is an ellipse. Okay, a couple of things about it. Think of it as a circle which has been squashed along one of the axes. So in this case, I've squashed it along the y-axis. An ellipse is defined by 2 radii. Okay, so here we have A, which is the distance from the origin along the x-axis to the edge of the ellipse. And here we have b, which is the distance from the origin along the y-axis to the side of the ellipse. Okay, so A and B are what we call radii of the ellipse. Okay, A is a major radius, B is the minor radius, whichever one's bigger, the major and minor. Okay, to draw an ellipse, what we do is we split it up into two regions, or we can't use 8-way symmetry as we did with the circle. We've only got 4-way symmetry. So what we do is we calculate the this quadrant, so in the upper right-hand quadrant, and we split the quadrant up into two regions, region 1 and region 2. Region 1 is when the gradient on the ellipse is greater than -1. So if I was to put a tangent line here, it would have a negative gradient, but it's quite a shallow negative gradient. As soon as we get to this point, where the gradient becomes less than -1, we're in region 2. So the ellipse symmetry, instead of having 8 points, I've only got 4 we can use. Okay, quite similar to the one before. As you can see, this is the ellipse point, and we've only got 4 of them. So it's plus or minus x, plus or minus y. Right, so let's proceed as before. So we use a Cartesian equation of a circle. This time we're going to use a Cartesian equation of ellipse. So it's slightly more tricky. So you've got the minor radii, or radius squared, times x squared, plus the major radius squared times y squared, equals a squared plus a squared times b squared. If we rearrange that to make y the subject, we get this expression. And we're looking for the point at which the gradient of the tangent changes from being less than -1 to being greater than -1. In other words, when dy dx is equal to -1. So we need to do a bit of calculus. Okay, so the only bit of calculus I think I'll ever do in this this unit, or the thing you might do some in, well, you might have done some in mechanics. Okay, so that's what that is this expression just written in terms of in terms of powers. It's exactly the same. So a to the power -1 is obviously the a to the power -1 is obviously that divided by a there. If you differentiate that, you need to use a bit of chain rule there and a bit of product rule, but eventually you get down to that. Okay, set that equal to -1, and what you want to do is rearrange to get x equals something. So not, a bit of an exercise, but not too difficult. So you get down to there. What do? I squared both sides to get rid of the square root. Obviously, the -1 squared goes to 1. Bx goes bh squared, x squared, a squared, and if I square that square root, just get rid of the square root. Multiply throughout by the denominator. Factorize out the x squared, etc., etc. So that's our point. That's our x coordinate at the boundary between the region 1 and region 2. Okay, so we need to calculate the initial error for region 1. Okay, so our Cartesian equation of ellipse gives us this expression. Okay, so this sort of notation means this is the error, the initial error for region 1. Okay, so if I plug in, well, that's the 12 o'clock position, and that's the first midpoint. I plug all that into there, find the difference, and I get this expression here. Clicker stopped working, I think it's run out of battery. Okay, the change in error, again, exactly the same as the midpoint algorithm. You take the midpoint 2 pixels along, you take that error and you subtract from that the error at the midpoint 1 pixel along. Essentially just lots of multiplying out and algebra. So you get down to this. Now, if the east pixel was chosen, we don't change the y, and that's our updated error. If the southeast pixel was chosen, we subtract 1 from the y, and that's our updated error. I'm going through this fairly quickly. It's just an exercise in algebra. It's not something I'm going to get you to do. For region 2, as I mentioned in the last lecture, we have to change the driving axis when we have a steep line. So in region 2, instead of going across in the x direction and calculating the error and then choosing whatever y coordinate I have, we're going to start going down in the y direction and choosing across, choosing which pixel to go to. So I'm going to go to the south or the southeast. Okay, so the change in error in region 2. So, okay, this is the error at the midpoint 2 pixels down, minus the error at the midpoint 1 pixel down. So remember, we're going down now rather than across. If the south pixel was chosen, our x coordinate hasn't changed. So we get the change in error. The x coordinate, if the southeast pixel was chosen, we've added 1 to our x coordinate. Again, just lots of algebra. It's not too tricky, hopefully. Okay, so this is what we get. So in the first region, this is our initial error, and those are our change in errors. In the second region, this is our initial error and change in errors. And in the same way, I'm not going to get you to do this, in the same way as we would do in the midpoint algorithm, just similar sort of program, we can get these ellipses. It allows you to draw ellipses. Now these are a lot more useful than circles because it allows us to draw more curves. And so when you're doing things like fonts and things like that, it allows us to draw curves. These sort of things are used for drawing packages. Whenever you want a circle on the screen. In fact, we don't in practice we actually use the midpoint algorithm when b is equal to a. It gives you the midpoint algorithm. So when a and b are the same, it's the same as the midpoint algorithm. Okay, right.